Okay, so atoms are too small to see, which makes them difficult to count. And then there's too many of them also. But we oftentimes need to know, at least in general, how many atoms we're dealing with. So we count them by weighing them. And this is something we do in everyday life too, and here the example is shrimp. So if you go to the grocery store and you want to buy some shrimp, what they're going to do is they're going to list them as with these funny numbers, like 41 to 50 count shrimp, right? What does that mean? That means that in 1 pound, there would be 41 to 50 of these shrimp. And if you had larger shrimp, you would have fewer number of shrimp in the pound, right? So, the big tiger prawns, the really big ones, their count might be 10 to 15. So a pound of shrimp, there might only be 10 shrimp because each of them is 1/10 of a pound. But regular shrimp, there might be 41 or 50 in there, somewhere in that range. So they're much smaller shrimp, right? You can count the shrimp by weighing them. So let's say, you're planning a party and you want to have, you want to be able to serve 5 shrimp per person, and so you need to have an idea of how many shrimp am I purchasing, right? Well, you're not going to go to the store and say, well, I want 375 shrimp, please. No, you pick a size, and then you can use the mass to count the shrimp, right? So if you got 2 pounds of the 41 to 50 count shrimp, then you would get 84 to 100. That doesn't, 82. I don't know if that's their typo or mine. 82, because 2 times 41 is 82. 82 to 100 shrimp, right? Everybody okay with that idea? So we do a similar thing for atoms, except we do it more precisely. Instead of having these categories of shrimp, we're actually going to be very specific about the mass of the isotopes, or the atoms. So chemists often need to know the number of atoms in a sample. And the reason is because chemical processes occur between individual particles. So 2 atoms of hydrogen and 1 atom of oxygen make 1 molecule of water. And the ratios of those are very precise, and it always works out that way. You don't have some water molecules that have 3 hydrogens. They all have 2. It's exact that way. So if we want to know the number of atoms in anything of a normal size, anything that you could see, we're going to count them by weighing them. When we count large numbers of objects, we often use counting units, such as a dozen. We are all very familiar with a dozen, probably haven't thought much about what dozen is or what it means or how kind of strange it is. A dozen means 12 things, right? You could have a dozen pencils, you could have a dozen eggs, you could have a dozen Krispy Kreme donuts, those sound kind of good right now. It's 12. It's 12 of anything, right? There's another object, another counting unit you may not be familiar with. It's a gross. Right? A gross of objects. I don't know how that came to mean something that was disgusting, but a gross of objects is a dozen. So it's a 144 objects. Another counting unit is a ream. A ream is used for paper. A ream is 500 pieces of paper. 500 pieces of paper could weigh 20 pounds or could weigh 5 pounds. It depends on how thick and good the paper is. But generally what you're interested in is the number of pieces, right? You want to know how many copies you can make. So it's a counting unit. Well, we have a counting unit in chemistry as well. But all those other units are way too small. We need something that's a much, much larger number. And so the chemist's dozen is the mole. So mole, it's not a little furry, short-sighted animal. It's not a yummy sauce. It's just mole. And it is abbreviated, which I think is totally stupid, but I can't change the chemical world, so we'll just have to go with it. The abbreviation for this very short word is MOL without the E. Okay. So a mole is an amount of stuff containing this number of particles. So, like we say, a dozen equals 12 things, right? 1 dozen would equal 12 particles or things. A mole is 6.02214 times 10 to the 23rd particles. Seems kind of like a random number, but it was chosen for a good reason. It's called Avogadro's number. So 1 mole of anything is Avogadro's number of units. They could be atoms, ions, molecules, particles. Okay? A mole of something is a usable amount. So here we have 22 copper pennies, and that is approximately 1 mole of copper atoms. Big enough to see, small enough you can hold it in your hand, right? Tablespoon of water, approximately 1 mole of water molecules. So now I just have to tell you a story because it's just too cool. Our 4th son is our mole baby because he was born on mole day. I'm a chemist, my husband's a chemist, and son number 4 was born on October 23rd. So 1023, like 10 to the 23rd, that's mole day. And the chemists actually do weird things like dressing up as moles and having parties and stuff. It's like Pi Day, right? March 14th or May the 4th, right? You know, we use the date as an excuse to celebrate something. So he was born on 10/23, and he weighed 10 pounds, and he was 23.5 inches long. This is kind of cool. It would have been really cool if he'd been born at 6:02 a.m. or 6:02 p.m. I did my best, but it didn't happen. It was more like 8:30. I mean, there's only so much you can do, right? So he's our mole baby, and that's just kind of fun. We actually said to each other, should we give him the middle name Avogadro? And then we said, no, we won't do that. So we named him after a Nintendo game instead. His middle name's Yoshiaki, after Yoshi's story.
That's cool.
Needed a Japanese middle name. Well, the other cool thing about that is his first name is Michael, and my husband likes to have fun with initials. So his initials are M-Y-K, which you could pronounce Mike, right? Yeah, so now I've told the internet what my son's name is. That's great. And he's the only one in the world with that name, so, oh well. Maybe I'll have to edit the video. Okay, personal story done. How did the mole get its specific value? Why is it that weird number? The number was chosen so that a mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. Now, does that definition sound a smidge familiar? An atomic mass unit is 1/12 the mass of a carbon-12 atom. So 12 grams of carbon-12 is this many 6.022 times 10 to the 23rd carbon atoms. Now, yeah, there's a 1,4 after that, and it's actually known a little further out than that, but for most purposes, 4 significant figures is enough, and so that's what we're going to use. Because of how these units were defined, a mole gives us a relationship between the mass in grams and the number of atoms, and it also gives us a relationship to the average mass of the atom. So this allows us to count atoms by weighing them. So converting between moles of atoms and number of atoms is the same sort of calculation as counting eggs. Any question?
Atoms per
It's the number, 1 mole is 6.02 times 10 to the 23rd particles, atoms. Yeah. So we know that a dozen eggs is 12 eggs, and so if you go to Costco, you can buy 5 dozen eggs. How many eggs are in there? 60. Well, how'd you do that? You did dimensional analysis in your head, and you could do that because it made sense to you. But we can also write it out. So 5 dozen, and we want to figure out how many eggs there are. We're going to use a conversion factor relating eggs and dozens. And we're going to have the dozen on the bottom because we want that unit to go away. And then we write, well, there's 12 eggs in 1 dozen, and then you do the math and you get 60 eggs. You can all do that calculation. You can all do these mole calculations. You just have to get your mind around it, because sometimes we get this block, right? It's a little bit like, sometimes when I'm walking on the sidewalk, I think, if there was a sheer drop-off on each side of this sidewalk, I'd have a hard time walking on this sidewalk. It's like 33, 35 inches wide. It's not a balance beam or something. I walk down the sidewalk all the time without falling over. But if suddenly there was, this huge drop-off on each side, you're going across the Grand Canyon on a bridge the width of the sidewalk without any guardrails. Right? If you didn't know there was a drop-off, if there was grass there, you can walk across that fine, right? But when you see that there's this huge drop-off, then your brain freaks out, and now you can't even walk in a straight line. That happens when you try to do math and chemistry, right? You all have the skills to convert dozens of eggs into numbers of eggs. And you don't freak out about it, because that's just regular stuff, right? There's grass. But then when we start throwing around atoms and moles and this crazy number, it's like there's this huge cliff, right? And you're going to fall off the sidewalk and die. So what you have to tell yourself is, I've got this. I can do this. Okay, so there's some psychological stuff in here that you just have to give yourself a pep talk. You're all capable of doing this. So to convert atoms and moles, we just use this factor. 1 mole of atoms is this number of atoms. And so we can put mole on top and the number of atoms on the bottom, or vice versa, turn it upside down. Let's do an example. Pure silver ring contains 2.8 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? So when you see atoms, think eggs. And when you see moles, think dozen. So I've got atoms, and they're asking me to find moles. This is dimensional analysis. We're going to identify what we're starting with and what we're going to end up with, and then figure out how we can get there. Do we have a relationship between atoms and moles? Yes, we did. I just explained that one to you. So we can do this in one step, because we know that 1 mole is 6.022 times 10 to the 23rd atoms. So we'll start with atoms. 2.80 times 10 to the 22 atoms. And I want moles up here and atoms down there. So the units work out. Units first. And then I need to put the number in here. And sometimes what students do is they'll put the number in the wrong place, because moles and atoms just, it's the cliff next to the sidewalk. A mole is like a dozen, and the atoms are like eggs. So you would never say that an egg is 12 dozen eggs, because that's silly, right? 1 mole, 1 dozen, is that many 12 eggs or atoms, right? So 1 mole 6.022 times 10 to the 23rd atoms. Then we have to do this on our calculators, which is another issue. And this number here is one of the reasons why we just have to become proficient with scientific notation. So remember that the EE button or the EX button on your calculator means times, well, actually I'm just going to write it in words, means times 10 to the. Okay? So to enter this in my calculator, 6.022 times 10 to the EE button, 23. I'm not actually going to type in times 10 ever. So get your calculator out and make sure that you can do this with me. There's one kind of calculator that's a little different, and if you've got one of those, we'll have to have private lessons. But what I'm going to do is 2.80, and as I hit EE, I say times 10 to the 22, times 1 if you wish, divide by 6.022 EE 23 equals. And thinking ahead, I should have 3 sig figs. So 4, 6, 4, there's 3, and I'm going to write down 2 extras. And the unit is mole. Avogadro's number here is not exact, but it's 4 sig figs. And what we're starting with is 3. So then this would round to 0.0465 moles. I had somebody ask me yesterday, is it okay to box or circle the answer? I'm like, yeah, that would be great. I actually prefer that. He's like, well, I was just checking because my calculus professor hates it when people do that. What kind of a weirdo is that? Those math people are very strange. That was you? Yeah. Well, it's always good to ask. Yeah. So I would explicitly say, please box it, and I don't care if you circle it or box it. I prefer boxing, but a box or a circle around your final answer, especially if you're handing in paper homework, it just makes that answer jump out at me, because oftentimes we have all of this scribbly work, and some of us are less organized than others, and let's make it easy for the person looking for your answers, right? Anybody having issues with their calculator? Yeah?
Yeah, I got that answer, but I got like 4.649. Did I have multiple something, right? I think I'm gonna miss it.
Okay, so that was converting between moles and atoms, but we need one more thing if we're going to weigh them, to count them. We need to know how the mass of a mole of atoms. And that's called the molar mass. Atomic mass is the mass of an atom. Molar mass is the mass of a mole of atoms. Okay? So this is where the convenience of the number choices and definitions comes in. An element's molar mass in grams per mole is the same number as the atomic mass in atomic mass units. So up there on the periodic table, like under, we looked at chlorine, 35.453. That is the average mass in atomic mass units of one chlorine atom. But if I have a mole of chlorine atoms, it's 35.453 grams. Okay? So that's on the periodic table. If you find aluminum on the periodic table, the average mass is 26.98 grams. That's the mass of 1 mole. That's Avogadro's number of atoms. Carbon, the average mass is 12.01. That's 1 mole of carbon, Avogadro's number. For helium, the average mass is 4.003 grams. That's a mole. That's Avogadro's number. And here, just to help us out, we've got pictures. So this is like the giant tiger prawns, right? And here we've got like the regular shrimp, and these are those little tiny cocktail shrimp. Like, how do they get the legs off those anyway? And so the number of pieces that you would get in a pound is going to be different. If you have the same number, then the mass is going to be different, right? So here we're looking at the same number of atoms, and the aluminum is going to weigh more because each of the atoms is bigger. Okay? So the molar mass of any element is a great conversion factor between mass in grams and amount in moles. So for carbon, from the periodic table, we see that 12.01 grams is equal to 1 mole, and we can make that into a conversion factor.
You were taking numbers for the
Mm-hmm.
why do we only take 2 significant numbers?
Oh, that's a good question. So what he's asking about is here 12.01 grams. It's got 2 decimal places, 4 significant figures. But on the periodic table up here, it says 12.0108. So why am I rounding that? That's an excellent question. In most of our calculations, the measurements are going to have 3 or 4 significant figures. And so then if we use 4 significant figures in the molar masses, we're not really affecting the number of significant figures. If we were doing more precise work, then we would definitely want to use all of the available digits. I heard about a chemistry instructor in the area who says, it doesn't matter if you round these or not, you can just round them to whole numbers. What? Well, with carbon, it wouldn't matter, right? If you round 12.01 and you just call it 12, like, not a big deal. What about chlorine? If you call that 35, it's not. It's like between 35 and 36. That's going to cause tremendous amount of error in your results, right? Like, don't do that. Well, do we have to write down all these digits? My opinion is 4 is enough for most purposes. The other thing that can be a little tricky and some students find very disturbing is if you compare this periodic table, say, with the one on the yellow card, with the one that you might find on the internet, you might find the later digits to be slightly different. Because these numbers are not exact, they're measurements, and they're based on relative abundances and stuff, and so they do change, they're revised occasionally. They take that very seriously, and they don't do it very often, but you will see different periodic tables where the mass of carbon is not exactly the same as the mass of carbon listed up there. So, my approach is use 4 sig figs. If that bothers you and you want to use more, God bless you. Absolutely, go for it. That would be better. When I started teaching, the book I had rounded them all to 4 significant figures, and I've got a whole bunch of them memorized to 4 sig figs, right? And so it's just a lot easier for me to use that, and there's just less digits to mess around with, and when it really doesn't matter, then we say it's okay. So that was an excellent question. Does that answer it? Yeah. So we get this number from the periodic table, and we can make 2 conversion factors out of it. And this also comes down to dimensional analysis. So we should be able to do things like this. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So pull out numbers. We got 35.8 grams of copper. And that's the only number, so that must be what we're starting with. And what are we supposed to get? Moles. So over here, we're trying to get to moles. Well, how do we get from grams to moles? The molar mass. So that we do that in one step. So 35.8 grams of copper. I'm just going to have one fraction, and my little path that I wrote out there tells me that I want moles on top and grams on the bottom, because then the units are going to work out. Grams per mole, that's the mass of 1 mole, that's the molar mass of copper, and we get it off the periodic table. 63.45? 54. 55. Close. That's the one I'm a little wishy-washy on. 63.55. Yes? That's a good question. Why am I not using Avogadro's number? Because I'm not looking for number of atoms. If I wanted numbers of atoms, I would use that. I'm just interested in how many moles. So this would be like, I've got 500 pounds of eggs, and each dozen eggs weighs, well, let's say I have 10 pounds of eggs, and each dozen weighs 1 pound. How many dozen do I have? That's the sort of calculation we're doing here. Yeah. So 35.8 divided by 63.55. And then I'm going to think ahead to how many sig figs. I started with 3. That molar mass is not exact, but it's more than 3. And so my answer is going to have 3 significant figures. 5, 6, 3. And I'm going to write down the next 2. And it's that many moles. And then I'm going to round it and say it's 0.563 moles. Any questions? Yeah, should I put moles of copper? Doesn't hurt. It's always correct to say moles of what. Sometimes it's not necessary. Like here, we're only talking about copper, but later on this semester we'll be doing a lot of things where we've got a lot of different substances, and so then yes, it is important to specify moles of what. So this type of calculation is like super, super, super important. Chemists do this all the time, grams to moles. 0.563. Okay, so now we have everything we need so that we can count atoms by weighing them. So you weigh a sample, and you convert the mass to moles using the molar mass, and then you can convert the moles into numbers of atoms using Avogadro's number. So the path here would be grams of element to moles of element to number of atoms, and the conversion factors we need are the molar mass and Avogadro's number. How many carbon atoms in a 1.3 carat diamond? Diamonds are a form of pure carbon. Well, 1.3 carats. Okay. It's not, rabbit carats. It's a unit for jewelry. Okay, great. What am I trying to find? Atoms. Atoms of carbon. Of course, I gave you that nice path, and then this one doesn't follow that, right? It's a little different. So we have to learn how to think about these things. Can we do this? Sure we can. Absolutely. Because it's a for practice problem, and if it wasn't doable, it wouldn't be in the PowerPoint slides. Nothing else. Okay, we're given this relationship here. A carat is 0.20 grams. Because nobody remembers that except jewelers, maybe. So this would allow us to go from carats to grams, right? Everybody okay with that? That conversion factor was just handed to us. Here it is. Use it. Okay, so now we're back into normal stuff. If I'm trying to get from grams to atoms, what do I do in the middle? Convert to moles. and then to atoms. You heard of the TV show Malcolm in the Middle? Think moles in the middle. So if you're making a path and you're not sure where to go, try moles in the middle. We'll find out that moles end up in the middle of lots and lots and lots of things. So we've got our path. Any questions about getting the path? Getting the path is the hard part. Now we just need to follow the path. It's like follow the yellow brick road, right? We just need to follow the path and we'll get to the wizard. 1.3 carats. I see 3 arrows. So I'm going to have 3 fractions. Carat, gram, moles, atoms. Carats, grams, moles, atoms. This always makes me think of Dora the Explorer. You guys watch that show? Yeah.
Did you argue to see the movie?
Probably not. I don't think my 10-year-old boy is interested in watching that. But yeah, they've got a movie coming out now. So I guess I can go back to using this analogy. Every single Dora episode, right? They had this problem where they needed to get from here to somewhere. And who do we call when we don't know which way to go? The map, right? And then the map comes out and does this little dance, and I can do that. And then they lay out how you get there. Well, you start at the carat, and then you go to the gram, and then you go over the snowy moles, and then you get to the number of atoms, right? And then they would chant, right? Carat, grams, moles, atoms, right? That's exactly what we're doing here, right? So the map, cute little map, gives us this. And then we take that, and that just goes straight into our equation, okay? I know some of you this has not clicked for you yet. Today would be a very good day to have this click, okay? And if it's not clicking in lecture, let's figure it out in lab. And once you see it, you're going to go, oh, it's so easy. Once you see it, it's very easy. So there's our path, and that tells us what to write in the numerator. And then we just take this unit and we put it in the denominator, because we're all about canceling out these units. I want that one to go away. I'm going to put grams down here, so that one goes away. And I'm going to put moles down here, so that one goes away. And I get all the units in place, and then the units are going to tell me where to put the numbers. There's no thinking, should I multiply by that or divide or which one's bigger? You just stick them with the appropriate unit. So this one's actually written out for us. 1 carat equals 0.20 grams. So 1 carat is together and 0.20 grams is together. So over here in this first one, I'm going to put the 1 with carat, because that's how it is in the relationship. 1 carat, 0.20 grams. And then I've got the 1 in the middle, and I've got the 1 at the end, and you don't have to put them in order. You can put them in whatever one comes to you first. You might say, oh, atoms and moles. I'm okay with that one, because I know that 1 mole equals 6.02 times 10 to the 23rd, in this case, atoms. Definition of Avogadro's number, definition of the mole. So 1 mole. 1 goes with mole, and this long number that I never remember to leave enough space for, so we have to kind of squeeze it in there, goes with atoms. That's a good question. Will I give you Avogadro's number on the test? Probably. But if you do all the homework and the worksheets, you'll have it memorized. Yeah. Then this one in the middle, we're like, oh, grams and moles. Maybe the periodic table could help us out. So there's a number under carbon in the periodic table. That's the average mass in atomic mass units of 1 atom. It's the mass of 1 mole in grams. So from the periodic table, I see that 1 mole of carbon is equal to 12.01 grams, so I lost the 1. 12.01 grams of carbon. 1 is with the mole, so I'm going to put 1 with mole, and 12.01, is with gram. So the map tells me where to go, I just have to follow the directions, and then the units tell me where to put the numbers, and now all I have to do is multiply and divide as I go across. 1.3 times 0.2. Divide by 1 times 1. Divide by 12.01 times, now let's use the button, okay? 6.022. And there's a single button, right? I showed some of you where it is. I'm going to press that and say times 10 to the 1 button push, 23 equals. And I get a number. And thinking ahead to how many sig figs I want to use, I see that the number I started with had 2 sig figs. And this conversion factor only had 2, and I've got 4 and 4, so I need to have 2 sig figs. 1.3, and I'll write down the next 2 digits, and then my calculator is saying E22, but that's calculator language, and when we write stuff, we use human math language. So write down times 10 raised to the power of 22, don't show me E. I know what that means, but it's like my son when he called the cash register the dollar biller. I knew what he meant, but if he did that now, he's 24, people would laugh at him, right? Oh, I know how to run the dollar biller. Yeah. So 1.3 times 10 to the 22 atoms of carbon in the diamond. Is that a reasonable number? It's not unreasonable. Now, if you do your math wrong, sometimes you can end up with 1.3 times 10 to the minus 50. Can you have less than 1 atom? Nope. So if you're doing something where numbers of atoms and you end up with less than 1, go check your math because you did something wrong. Okay. Any questions? So just a little thinking. How big is Avogadro's number? My kids have a book called How Much is a Million? Which is, even a million just kind of boggles your mind. It talks about how far, spaghetti end to end would go to the moon and back or something crazy. This is bigger. This is bigger than the national debt. Way, way bigger. So if we had Avogadro's numbers of pennies, it would cover the Earth's entire surface to a distance of 300 meters. That's like the length of 3 football fields deep. The whole Earth covered in pennies. That's a lot of pennies. It's a big number. If you had Avogadro's number of grains of sand, those are a lot smaller than pennies, it would cover the state of Texas to a depth of several feet. If you counted 24 hours a day, as fast as you could, for the rest of your life, you could not get to that number. So obviously, actually counting atoms just doesn't work out. And there we have it written in decimal notation. It's a whole bunch of zeros. So Avogadro's number is super, super big. I think is this the last one? Last one. Last example. I'm done with chapter 2. Titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. Okay, this is one of those ones that you're like, what the heck? We can do this. This requires thinking and the units are going to help us out. Okay? This is not unlike the one with the Antarctica and how much does the ice weigh that I gave you on that worksheet. Okay, so we're going to pull the numbers out and write them down. So 2.86 times 10 to the 23rd atoms. What kind of atoms are those? Titanium. So I'm atoms of titanium. And then the other number I'm given is density, 4.50 grams per cubic centimeter. Now it's typed there with a slash, but I want to write it as a vertical fraction. So my brain recognizes, oh, that looks like a conversion factor, doesn't it? It's grams per 1 cubic centimeter. Okay, good, we wrote down the numbers. Then let's figure out, what are they asking us to find? The edge length of the cube. Well, that's not a unit. Well, let's draw a cube. There's words that we use that we don't really recognize the distinction between. I think in everyday language, square and cube are kind of interchangeable, right? But a square is a planar object, it's two-dimensional. A cube is three-dimensional. What is the edge length? Well, what do we often use for the edge length of a cube? L, right? Length. So L, in a cube, they're all the same. Is there an equation that we know that has the edge length in it? Yeah, we calculate the volume, right? So the volume of a cube is the edge length cubed. Okay, that doesn't seem to be getting us anywhere. So that's at the end of what we're trying to find. So maybe let's look at the beginning where we're starting and see if that could possibly give us some clues. So I have two numbers here. This one is atoms and this one is grams per cubic centimeter. I'm not sure what to do. I'm going to pick the one that doesn't have per in it, because this could be used as a conversion factor. This one cannot. So this is probably what I'm going to start with. So I'm starting with atoms, and I need to convert that into something. And then ultimately, what would be a good unit for this length? Maybe centimeters? It doesn't specifically say, but maybe centimeters. What's going to be in the middle? Moles. Moles in the middle, right? So I could convert atoms to moles, right? Using Avogadro's number. And I'm still missing some pieces. We could look at the units of this thing over here that, since they gave that to us, we're probably going to need it. There's grams and cubic centimeters. It's cubic centimeters, this is centimeters. There's a relationship here that allows me to calculate volume in terms of centimeters, right? So let's put cubic centimeters here, and then I'm going to use that equation to get to the length. This is a problem where we're mixing dimensional analysis with an equation. So what's missing between mole and cubic centimeter? The mass in grams. I can do moles to grams using the molar mass of titanium, and the grams to cubic centimeters is the density. Once I get cubic centimeters, I can use algebra to find the length. This is one of those problems that involves problem solving and critical thinking, and there will be questions somewhat like this on the exam. On every exam, there'll be a question that requires you to put stuff together that you haven't been spoon-fed. You have to take the tools and put them together in a new way. Okay, so now I got a path. Atoms to moles to grams to cubic centimeters. And you hear Dora just chanting that one. 2.86 times 10 to the 23rd atoms, titanium. I've got 3 arrows. Oops, ran into that. That's okay. Atoms to moles to grams to cubic centimeters. Atoms to moles to grams to cubic centimeters. Put atoms down here, so that unit cancels out. And I'm going to put mole down here, so that unit cancels out. I'm going to put gram down here, so that unit cancels out. I got all the units figured out. Now I put the numbers in. The units are going to show me where to put the numbers. Well, this guy's just sitting out here waiting to do something. That's going to go over here where I've got cubic centimeters and grams. Right? So 1 cubic centimeter, so that's on the top, and 4.50 grams. And then this guy, moles to atoms, what's the number that goes there? 6.022 times 10 to the 23rd. So a mole is like a dozen, so it's 1 dozen. And the atoms are like eggs, so that's where the number goes. 6.022 times 10 to the 23rd. And then grams per mole, that's the molar mass from the periodic table. So we find Ti, not to be confused with TL, 47.867. I don't have that one memorized, so we'll just use all the digits that were up there in the periodic table. Now it's a matter of sticking it into your calculator. Just go left to right. That way you don't have to write down any extra stuff. Multiply by the top, divide by the bottom. And I'm thinking this needs 3 sig figs. And the unit is cubic centimeters. Am I finished? No. That got me the volume, and now I need to use algebra to calculate the length. So I'm going to take my equation, volume equals the length cubed, and I think it's always a good idea to rearrange the equation first and then plug the numbers in. So I need to solve this for length. Well, I've got length on one side, but it's cubed. I need to get rid of that. So I get rid of that by taking the cube root of both sides. So the length is equal to the cube root of the volume. I want to use my unrounded. I've got extra 2 digits on. I'm going to use that one here. I'm going to take the cube root. So I don't use that button very often. This would still have 3 sig figs. I can check to make sure I use the cube root button correctly by multiplying this by itself 3 times. Yeah, and I get to 5.05 back, so I did it right. Now I can round this, and it's 1.72 centimeters. Any questions? Let me check the answer. Whoops. Yeah, 1.27. 1.72. Any questions?